Welcome everyone to the Tom class. In the last class, we have studied the gyroscope chapter, and today's session we will study the flywheel and governors. Okay, um, flywheel is a very small point topic you have for your syllabus, and then governor will study, um, which is also not that big compared to like the first couple of chapters which we have studied. Okay. So let's start with definition of the flywheel. Can anyone tell me like what is the meaning of flywheel and why we use it? Um, can anyone tell me what is flywheel or under what situation you use it? Yes, it is used to store the energy. So in general, or I can say that the proper definition would be a flywheel is used to control the variation in the speed during each cycle of the engine. During each cycle of the engine of an engine. Okay, so this last word is very important. Cycle of the engine. And can you tell me what is governor? Can anyone tell me what is governor? That is the main reason we are studying these two topics together. Uh, can you tell me what is governor? Is it also doing the same thing like um, controlling the variation of the speed? Yeah, but it is little different from the flywheel. Okay, so flywheel also um, control the variation of the speed. Governor also controls the variation of the speed, but their application is for different purposes. Okay, so flywheel we are using to control the variation in the speed during each cycle of the engine. Okay, uh, suppose let's say if we take a single cylinder engine, okay, like like let's take a four-stroke engine. In that case, we have suction stroke, compression stroke, then power stroke and exhaust stroke. Correct. So these are the four strokes we have, and we can clearly we know that in out of all these four strokes, only in the power strokes we get the energy out. Rest of the three strokes, there is no output energy. Basically, we have to give some energy. Okay, we need energy, you can say. In compression, we need energy. In expansion stroke, sorry, in exhaust stroke. So what we can understand, okay, I'll share my screen again. Just give me a minute. How about now? Can you see my screen? Yeah. Okay. uh, I was talking about the each cycle of the engine. Each cycle of the engine consists of suction stroke, compression, expansion, or you can say power stroke. exhaust stroke. Correct? These are the 4 strokes of the engine which completes a cycle, right? So, and we know that we have to make sure that our engine is running smoothly in all these 4 strokes. It's not like um, it is running fast during power stroke and in rest of the stroke it is running slow. So um, in each cycle of the engine, we expect that um, our engine should run smoothly, right? So basically, we are trying to avoid the fluctuation here. Let's take a simple example of this is turning moment diagram of a single cylinder 4-stroke engine. Okay, so this is single cylinder 4-stroke engine. Okay, as I already mentioned, there are the name of the 4-stroke: suction, compression, expansion, and exhaust. And we we have only one cylinder. Okay, and these are the on x-axis we have the crank angle. When crank angle is 180 degree, we have completed the suction stroke. When crank angle is 360 degree, that is 2 pi, we have completed compression stroke. Okay, um, so it's a 4-stroke engine. We have separate stroke for each suction, compression, expansion, and exhaust. Okay, and on the y-axis we have the turning moment here. So this is called as a you can say a turning moment diagram, where we have a turning moment versus the crank angle. Okay, so if we are getting a turning moment positive, what we can conclude out of it, and if turning moment is negative, what we can conclude out of it is what you should know. So you can clearly see in this figure, in the expansion stroke the turning moment is positive. Okay, so basically in case of expansion stroke, that means a power stroke. We are getting a energy in that stroke, right? So uh, the turning moment is generated during that stroke, you can say, or the energy generated during that stroke. And in rest of the 3 strokes, which are suction, compression, exhaust, you can clearly see uh, the turning moment diagram is on negative side. Okay, so in case of 4-stroke internal combustion engine, this diagram is uh, you can use for 2 complete revolutions of the crank. 2 complete revolution means 4 pi, 1 complete revolution means 2 pi. Okay, and you can clearly see that in suction, compression, and exhaust, more or less our turning moment is negative, whereas in exhaust or expansion stroke or power stroke, we have the positive value of it. So you can clearly see here that there is very much fluctuation in the energy. Do you agree? There is a lot of fluctuation in the energy because we are using a single cylinder, and turning moment, let's say, or the energy in this case, here or here or here, it's quite less, or there is a variation, a lot of variation we can see um, in the energy which we are getting during different strokes. Okay, so what will happen if I connect a lot of single cylinder engines together and we call it as a multi-cylinder engine? Okay, we generally use it in heavy vehicles. So multi-cylinder engine, right? So can I expect the similar diagram there, or will it be little smooth compared to the first diagram? Yeah, it will be little smooth because we know, like, uh, we whenever we do the balancing of the engine, we know we don't put like um, let's say, power stroke of all the engine at a time. Okay, we use some ratio in order to do the balancing. We'll study that in a balancing of engine topic. Okay, but as of now, you should know that if you are using a multi-cylinder engine, the power stroke of all engine will not appear or occur at a same instant. Okay, so at some instance, power stroke happens for, let's say, two engines, and after that power stroke happens for next two engines. So basically what we are doing is we are balancing out the forces when we do the multi-cylinder engine. And because of that, what will happen is, um, at any instant, if you want to calculate the crankshaft torque, okay, or torque means like or turning moment, basically it's given by sum of the torque developed by each cylinder. So we'll do the sum of the torques developed by each cylinder. Okay, so suppose this is the turning moment diagram first cylinder, then let's say turning moment diagram second cylinder might be like this. Okay, turning moment diagram of the third cylinder might be something like this. Okay, um, and fourth and fifth and sixth and so on. Okay, so ultimately what I'm trying to convey you is um, like in case of multi-cylinder engine, if you just take a sum of it, okay, for each stroke, let's say here if you do the sum, here you do the sum, here you do the sum, and here you do the sum for each individual cylinder, what you will end up with is sum of the torques developed by the each cylinder. If you add, you will get a crankshaft torque at that instant. Okay, and your diagram will be look like this, little smoother. Okay, so there is a less variation um, compared to the initial line AB. Okay, suppose here AB is, you can say, the mean torque. Okay, A to B is the mean torque, and you can clearly see there is a little bit variation we have here, and C, D, E, F, G, H are the, let's say, wherever it is intersecting at a different angles, let's say pi, 2 pi, 3 pi, 4 pi, so on. Okay, so what we can conclude out of it is, uh, as you go on increasing the number of cylinders, we can expect uh, the variation for different crank angles. The variation in the torque is comparatively lesser, because the total crankshaft torque at that instance will be sum of the torques developed by each cylinder. Okay, and as we are having the different strokes for a different engine at a time, the curve is little smoothed out. But in case of single cylinder engine, we can clearly see that that is not the case. We cannot, like say, we cannot avoid the variation here. We get power in power stroke. Okay, we get energy in the power stroke, but we need energy in rest of the strokes. Okay, so the fluctuation of energy is a lot in case of a single cylinder engine, whereas in multi-cylinder engine it is comparatively less. So flywheels are very important for the single cylinder engines. Okay, so I used word fluctuation of energy. So let's try to understand what is the fluctuation of energy, like for different crankshaft positions. In from the figure number B, we will try to trace it out. Okay, so the second figure we'll use to understand the fluctuation of the energy. You can clearly see here A1, A2, A3, A4, A5. These let's say these are the little fluctuations compared to the mean torque, right? Where A1, A3, and A5, this one, and this one are the areas where these are the areas where, like, you can say the torque developed is above the mean torque. Okay, above the mean torque AB. And so we can expect that in this area A1, A3 and A5, our flywheel will store the energy. Okay. Whereas in the other areas like A2 and A4, these, and even A6 here. So in these areas, what we expect that in these areas, the energies are, or let's say the turning moment is below the mean turning mean torque, that is AB, and we expect flywheel to give the energy. Okay, so what flywheel does is flywheel stores the energy when excess amount of energy is developed about the mean value, so that is A1, A3 and A5 region, and it gives the energy whenever it is required, and those regions are A2, A4 and A6. Okay, in the same way, in the first figure, if you figure number A, if you see, what fly will do is it will store the energy during the expansion stroke and use the energy in the rest of the required strokes. So I'll go to the next slide now to make a chart. So at position number C, so let me just try to draw it here. Okay, this is C, this is D, E, F, G, H. Okay, this is A. This is A1, A2, A3, A4, and A5, and A6, for example. Okay, again this point is suppose C, and this is the same figure is repeating again and again, C2, H. Okay. Now uh, at point C, at crank position C, let's say E is the energy in the flywheel. Okay, E is an energy with the flywheel. At point D, what we can expect is A1 energy will be added to the flywheel, so it will be E plus A1. At point E, what we expect, we have added energy A1, but we have subtracted A2 energy out of it, so it is E plus A1 minus A2. Then we have added at point F, we have added the A3 energy. Then we have subtracted A4 energy at G point, okay, from it. Then we have added, by the time we reach the H point, we have added A5 energy to it, and by the time we reach the point C again, we have subtracted A6 energy out of it. So ultimately, how much is the variation in between? This is the final value, and this is the initial value. From the two values of the energy of the flywheel corresponding to the position C, which is initial and final, we can conclude that A1 plus A2, A1 minus A2 plus A3 minus A4 plus A5 minus A6, this has to 0. Okay, this is equal to 0, we can say, because ultimately we are reaching the same point. Okay, these 2 points are same, so ultimately we can say that whatever energy we are taking, the same energy we are giving here. So sum of all the energies will be 0. Okay, are you following till this? So out of this, we don't know A1, A2, A3, A4, A5, A6, they will have some different values. Okay, we cannot say that energy at E is the lowest or energy at F is the highest. That is depending on the value of A1, A2, A3, A4, A5 and A6. But what we can conclude here is the greatest energies of this is called as the maximum kinetic energy. Okay, so the term is maximum kinetic energy. And one is minimum kinetic energy. Okay, the greatest of all these energies is the maximum kinetic energy of the flywheel, and corresponding crank position. You can say the speed is maximum, and the minimum, let's say the least of the kinetic energy of the flywheel you will get, corresponding the crank position, you will say you'll get a minimum speed there. Okay, so minimum kinetic energy and maximum kinetic energy corresponds to the maximum. So this corresponds to the maximum speed because kinetic energy is um, half of I omega square, right? So it's I is same, though omega is only changing, so it's corresponds to maximum velocity or speed, let's say. This corresponds to minimum speed. Okay, and the difference between this maximum speed or the maximum kinetic energy to the minimum kinetic energy is energy stored in the um, is like maximum energy which can be stored in the flywheel. Okay, so that is delta E. I would say it is the energy stored in the flywheel. Okay, the difference between maximum and minimum kinetic energy of the flywheel is known as maximum fluctuation of energy. Okay, that much will be the maximum fluctuation of the energy. Uh, or we can say that much amount of energy we can store in the flywheel. Okay, and okay, so let's try to calculate this delta E through some formulation. Okay, can I proceed to the next slide? We'll start with a simple example. Let's say we have a flywheel. Okay, um, and let's say um, for example, this flywheel rotates at a maximum speed of omega 1. Okay, max speed, and omega 2 is minimum speed, for example. Okay, so maximum fluctuation of energy, I can say delta E would be half of I omega 1 square minus half of I omega 2 square. Correct? We can write it like this. Difference in the maximum kinetic energy and minimum kinetic energy will be the maximum fluctuation in the energy. Correct? As I already explained, minimum kinetic energy will be corresponding to the minimum speed of the flywheel. Maximum kinetic energy will be corresponding to the maximum speed of the flywheel. Okay, so from this I can take half of I as a common, omega 1 square minus omega 2 square. You will get. Okay. Okay, half of I omega square. I is nothing but your mk square. Okay, mass moment of inertia. I is equal to m is a mass and k is a radius of gyration. Okay, um, so this you know. Omega 1 square minus omega 2 square, you can relate it to like a square minus b square formula. A square minus b square is equal to a plus b and a minus b. So I can split this equation or this part into omega 1 plus omega 2 and here omega 1 minus omega 2. Okay, this 2 I will write here. Sum of the omega 1 plus omega 2 divided by 2 will be a, you can say, average, or you can say mean speed. I omega 1 minus omega 2 is delta omega. Okay, so here omega is a mean speed. Okay, omega is a mean speed. Okay, so there is one term, so this delta omega, which is omega 1 minus omega 2. Okay, so if I multiply with omega and divide with omega, this formula will further change to I omega square delta omega by omega. Okay, by multiplying and dividing with omega. Okay, I omega square delta omega by omega. So that is your delta I. I'll go to the next slide. I'll repeat here. We got I omega delta omega, and then we got I omega square delta omega by omega. Delta omega by omega is nothing but the K. And what is this K? Coefficient of fluctuation of the speed. K is equal to delta omega by omega. This is coefficient of fluctuation of speed. So what is the meaning of it? Change in the speed with respect to the mean speed. Okay, so it is a ratio of maximum fluctuation in the speed of the speed divided by mean speed. Okay, that will give you the K. So I can write it as I omega square K. Okay, I omega square K. And you can later calculate K is equal to delta E by I omega square. So the value of K you can calculate as delta E divided by I omega square, and so on. So you can further simplify it if you want. Because see, delta E, if you keep it as it is, divided by I omega square, you can multiply by 2, divide by 2. Okay, so what is the formula for this? Half of I omega square is what? It's half of I omega square is our um, mean kinetic energy, can you say, or the mean energy, because omega is our mean speed. Okay, so corresponding to that energy will be our let's say a mean energy, correct? So can I write it as like delta E divided by 2 times E? Okay, E is energy corresponding to the omega. Change in E, delta E divided by 2. So K can also be written as delta E divided by E. Okay, so one more point here I would like to explain that what is this K? K is our coefficient of fluctuation of the speed, that is delta omega by omega. So here we got one term delta E by E. Delta E by E is nothing but, similarly you can write it as, that is change in the energy, or the let's say maximum fluctuation of the energy to the work done per unit cycle, or the mean energy in general, um, will give you the coefficient of fluctuation of energy. This is coefficient of fluctuation of energy. You can write it as KE also, you can say. So this K can be written as KE by 2. Do you agree? So this relation we can make here, that coefficient of fluctuation of the speed is half of the coefficient of fluctuation of the energy. Okay. So these formulations are very, very important. I will collect everything on the next page now. So what is K? K is a coefficient of fluctuation of the speed, delta omega by omega. K, coefficient of fluctuation of the energy, delta E by what is delta E, maximum fluctuation in the energy, that is equal to I omega delta omega. We have further made it as I omega square K. Okay. And we know that K is equal to Ke by 2. Okay. This is all. These formulations you should know. Okay. All the formulas I have collected here. And what is omega? Omega 1 plus omega 2 divided by 2. What is delta omega? Omega 1 minus omega 2. What is omega 1? Maximum speed. What is omega 2? Minimum speed. Okay, is it clear till this? So, will you be able to calculate the energy stored in the flywheel? If question comes in exam, how much energy will be stored in the flywheel if they have given you the I value and omega 1 and omega 2 values? Yes, okay. And let's say if they have given you the delta E value, that is maximum energy can be stored, and let's say um, they are asking you some other things like radius of gyration, or maybe the mass of the flywheel. If omega n1 and omega 2 is also given, then I hope you should be able to calculate it. Okay, because same formula you can use. All the questions on the flywheel can be solved by using this small formulation. Okay, I have given a complete derivation to you in order to make you feel comfortable, like how all these terms, that is maximum fluctuation of energy, coefficient of fluctuation of the energy, coefficient of fluctuation of the speed, all are um, linked to each other. Okay, is it clear till this? Let me know if you have any doubt. Okay, if no doubt, then I'll open another presentation of the for the topic governors. Okay, so write down heading governors. Can anyone tell me what is the difference in flywheel and governor? Roughly, you can say in few words. What do you think? Like, are they same or are they different? Yes, one of them is used to regulate the load variation, other used to regulate the um during this cycle. Correct, because like, let's say if we are in the bus, okay, or the truck, a truck is fully loaded, then the load on the engine will be more at that time, and let's say it's half loaded, then load will be less compared to the first, and it's not at all loaded, then again the operation load on the engine will be less. Correct. So basically, fluctuation in the speed just don't come because of this, let's say, um, during each cycle. Like we know in the each cycle we have different strokes, and it will have a different variation in the speed. But that is one part, that's correct. But variation in the speed also comes from the variation in the load. Okay, and that is good point you have mentioned here, uh, Shruti. So governor is used to regulate the speed under the action of load, fluctuating load. Okay, so function of the governor is to maintain, write down, function of a governor NORS. NOR. Function of the governor is to maintain the speed of the engine, yes, within specified limits. Okay. uh, Under the action of different loading, whenever there is, or you can say whenever there is variation of load. Okay, so fluctuation of speed, again we are using the same word, fluctuation of speed. And as I already mentioned, the fluctuation of the speed can come during each cycle, and the flywheel is capable of handling it. Whereas the fluctuation of speed, as I mentioned, also can come from the variation in output torque of the engine. Okay, or basically load variation. Load variation, and governor will able to handle it. Okay, is it clear till this? Have you understood the difference? Okay, so can I say, like, so let's say if you are fitted a governor in let's say bus or truck, whether it will let's say operate continuously. Let's say we have a truck, and that is loaded, and it's running on a highway, okay, with certain speed. Whether this governor will be acted or active during that time, or is it working on that time compared to because there is no change in loading, right? So in that case, like it in each cycle, governor will not work. Governor will work intermittently. Let's say something is happening, loading, you are changing, okay, you are changing the gears, shifting the gears, or let's say you are loading the changing the load in your machine. In during those phase itself, let's say the fluctuation of the speed is controlled by the governor. But the flywheel the work of the flywheel is continuous, right? The flywheel has to work continuously in each cycle. That is also the main difference, you can say. So the operation of the flywheel is continuous, whereas the governor is more or less intermittent, we can say. Okay, flywheel is doing continuous work. Okay, whereas governor is intermittent. Whenever required, it will do work. Okay, because let's say if we have a vehicle which is running at a constant speed, um, with a constant loading, we don't governor will not be, let's say, working at that time. Okay, it is just at certain speed it will, um, at certain, let's say, um, there is no need of governor to be active or inactive in that time. Okay, so it will not operate in general way, we can say. But if you see, let's say I have given you the example of single cylinder engine and multi-cylinder engine. In multi-cylinder engine, I would expect that there is very less fluctuation in the, um, let's say, the energy compared to the single cylinder. So it is worth using flywheel only in the single cylinder engine, where we see the large fluctuation in the energy. Okay, so a flywheel may not be used if there is no, let's say, a lot of cyclic fluctuation in the energy output. But governor is always essential in all type of energy. Okay, because we have to adjust the supply and demand. Okay, how much torque we need depending on, let's say, um, depending on for different loading we need different torque, and governor is necessary. Okay, irrespective of what you are doing, whether you are using single cylinder or multi-cylinder engine. Are you following these points? Yeah. So the first case is like a flywheel is operating during each cycle, so it is doing a continuous work. It may not be required if the fluctuation of the energy is less, which is the situation in multi-cylinder engine. Whereas wherever it is, let's say, a fluctuation is large, in those cases we should use the flywheel. Whereas the governors maintain the speed of the engine in the specified limit whenever there is a change in the variation of the load. Okay, and so it is doing an intermittent work, and it has to match the supply and demand, so it has to be required in all kind of applications. Okay, I hope it's clear till this. So let's take an example of engine. What we are doing, if load on the shaft you are increasing, the speed also, what will happen? If you increase the load, speed will reduce, right? Speed of the engine will decrease unless and until you increase the fuel supply. Speed or the operating speed will not, you can say, increase. Okay, and how we increase the supply of fuel? By opening the um, fuel supply. Okay, by opening the throttle wall of the fuel fuel pipe, you can say. Okay, I'll repeat. So if you are increasing the load, let's write here load. If you are increasing, what will happen? Speed will reduce, but you want to maintain the speed. So in order to maintain the speed, what you need, you have to increase the fuel supply. And how you increase the fuel supply? You increase the fuel supply by opening the throttle valve. Okay, so should be handled by increasing fuel supply, and how you'll increase the fuel supply? Opening the throttle valve. Okay. On the other hand, let's say if load is reduced, the speed is high. Okay, the speed will increase, and this increased speed is handled by lowering the fuel supply. Okay, um, should be handled by lowering the fuel supply. Okay, and how you lower the fuel supply? By closing the valve. Closing the okay. So I will yeah, maybe, yeah, let me rub here and write correctly, write in a better way in the next slide, because the next slide will help you to understand in easily rather than writing on the same slide. So you can clearly see, so this is an engine. So if you increase the load increases, speed is reduced. Okay, and handled by um, increasing the fuel supply. And how you'll do this? Opening the throttle valve. Okay, so if you open the throttle valve, opening throttle valve means if you rotate this throttle valve to this, let's say a 90-degree angle, okay, like this, then it will fully open. Fuel supply will be more. So if fuel supply will be more, then again you can increase the speed and basically maintain your speed. Okay. On the other hand, if load is reduced, speed will increase, and this is handled by we should decrease the fuel supply. Okay, and how will you decrease the fuel supply? Closing the throttle valve. Okay, this means we are trying to make this throttle valve horizontal in order to lower the fuel supply. Okay, so I hope you understood how exactly this is different from the flywheel and how it operates. Okay, so basically ultimate aim of the governor is to operate the throttle valve. Governor is used to operate the throttle valve. What governor does is operate the throttle valve, and indirectly it is so by operating the throttle valve, we are controlling the fuel supply, and by controlling the fuel supply, we can either increase or decrease the speed of the engine. Okay, so this is how they are linked to each other. Okay, is it clear till this? Any doubt till this? Okay, so there are two types of governors. Governors are of two types. One is let's say types. First type is centrifugal. Second type is inertia. Okay, centrifugal governor and inertia governor. Okay, so let's try to understand them in detail. What is centrifugal governor? This is more common type. So centrifugal is commonly used, and its action depend on the change in the speed, so name itself indicate basically because of the centrifugal force, this governor will operate. Okay, so let's look into this figure. What we have is, we have some pair of the masses, let's call them balls, which are fixed to the arms, right? And whenever this let's say this is a spindle, when you rotate the spindle, what will happen? uh, if you rotate at a constant speed, then the distance between two balls is same, okay, will remain constant. But if you increase the speed, what will happen? The balls will try to move away from each other because of the centrifugal force, and indirectly it is lifting the shift, indirectly it is lifting the sleeve. And if sleeve is lifted up, okay, what will happen? It will close the throttle valve because speed is increased and it's time to close the throttle valve. If speed is reduced because of higher loading, then these two balls will come closer to each other. This sleeve will go downwards and it will open the throttle valve, making sure we have enough amount of fuel is flowing through this throttle valve, and which will help to increase the speed. Okay, I hope you understood the centrifugal governor, which is more common. The action of the governor depend on the centrifugal effect basically. Okay, I'll repeat, the action of the governor depend on the centrifugal effect produced by masses of these two balls. Write down again, I'll repeat, the action of the governor depends upon the centrifugal effects produced by masses of these two balls. Okay, as I already explained, if speed increases, the masses will go away from each other and upwards, sleeve will move upward, throttle valve will close. If speed is lowered, balls try to come together, so because of the smaller centrifugal force, and sleeve will come down, throttle valve will open in order to increase the fuel supply, in order to increase the speed. Okay, so this is how we maintain the speed, by using the centrifugal action of the masses of these two balls. I hope it's clear till this. Second type is inertia governor. Okay, in this type of the governor, the balls are affected by the forces set up by an angular acceleration and deceleration of given spindle in addition to the centrifugal force. Okay, I'll repeat. So in case of inertia governor, inertia plays an important role. Okay, so basically what will happen is, because the inertia, we know that angular acceleration or deceleration will produce. So the movement of the throttle valve is not just controlled by the centrifugal force, but also the angular acceleration and the deceleration of the spindle. Okay, so I'll repeat, in this type, the position of the balls is affected by the forces which are set up or created by the angular acceleration or the deceleration of the given spindle, in addition to the centrifugal forces on the balls. Okay, at the end of this chapter, we will study how this inertia governor looks. More commonly, we use the centrifugal governor. Okay. So what we should understand from here is, in case of centrifugal governors, we use a centrifugal force, and centrifugal force is depending on the engine speed. So changing the engine speed will, we can say, used to operate the centrifugal governor. Okay, whereas angular acceleration means change in the speed, angular speed, right? So basically, change in the speed is used in case of inertia governor. Not just the speed, but change in speed is also used in the inertia governor. So inertia governors, you can say, are a little bit faster compared to the centrifugal governors. Okay, so this is the introduction. We will try to go through different types of centrifugal governors, and then at the end we'll see how the inertia governor will work. Okay, can I proceed to the next slide? Yeah. Okay. So let's start with a simple example, a Vac governor. So it's again a centrifugal governor, or you can call it as a Vac governor. We have already, this figure number A shows how it looks. Okay, so we have a pair of ball of masses M attached to the links here. At point A, we have attached to link OA and AB. At point D, we have attached to the links OD and DC. Okay, we have these top two links are attached at point O. So O is the pivot point where we have pinned these two links. Okay, and we have an horizontal link BC to connect the rest of the AB and CD links. Okay, so this you can convert like this, or this you can convert like this. So rather than, if you replace this single point by with a link EF, you can call it as open arm type. What this is, open arm type Watt governor, and this is close arm type Watt governor. In second case, what we are doing is we are making a crossed arm. You can call it as a crossed arm rather than not close, it's crossed arm type Watt governor. Okay, so they are just two different types of it. Our focus will be on the first figure A itself, but the figure B and C are more or less same. Okay, it's just a different type of it. Okay, so let's now focus only on figure number A. I just explained how B and C is generated. If you replace point O with the horizontal line EF, you call it as open arm type, and if you cross the arms and write create a link FE, you call it as a cross arm type Watt governor. Okay, so let's try to understand figure number A now. So as the spindles are rotating, balls will take the position. Depending on whether the speed of the spindle is increased or decreased, arms will move, let's say, away from each other or towards each other because of the centrifugal forces. Okay, so just to let you know, here small m is the mass of ball, mass of each ball. H is the height of the governor. Okay, W is weight of each ball, is mg. Omega is angular velocity of arm sleeves. So this is omega. Angular velocity. Okay. So I'll go to the previous figure. So angular velocity of the spindle will be same as angular velocity of the sleeves. That will be the same as the angular velocity of the balls. Okay. So I'll just use word angular velocity. Okay. It is angular velocity of the balls, arms, and sleeve. T is the tension in the arm, Okay, why it is we are drawing a free body diagram of point A. just to make sure what are the forces will get applied on the arm. R is the radial distance to the ball center. Okay, this is the R. The radial distance from ball center to the ball center and the sleeve center. Okay, so these 2 points is R. Okay, yeah. So assume that these links are massless and you neglect the friction of the sleeve. Okay, and what we can say, how this point A will look like under the action of equilibrium. So point A will have mg force in a downward direction, mr omega square force, which is centrifugal force in outward direction, and T is the tension in the upward direction. Okay, so if I split this tension into the two components, T cos theta and T sin theta, I will be able to write. I'll go to the next slide, or let's write here itself first. T cos of theta is equal to mg, and T sin of theta will be equal to mr omega square. Okay, I hope you understood how I have written this. So if this is T, this is your T cos theta, and this side your T sin theta. So I'm just equating the forces. You might have studied this in mechanics. So the ratio of this will be a tan theta. Okay, T sin theta by T cos theta is T tan theta. So tan of theta can be written as mr omega square divided by mg. Dt will get cancelled, will get cancelled. So it's r omega square by g. Tan theta can also be written as r by h. Okay, so this is your r and this is your h. So r by h is tan theta. Okay, so you can say h is equal to r g divided by r omega square. So rr will get cancelled. So it's rr will get cancelled. So h is equal to g by omega square. Correct. And I'll go to the next slide now. H is equal to g by omega square. But what is omega? 2 pi n by 60. 2 pi n by 60 square. So it is 60 square divided by 2 pi square. We can write it like this. G is 9.81 divided by n square. So if you solve this, 60 square divided by 2 pi into 9.81, ultimately what you can end up with is 895 by n square in meters. So this is the height. Okay, so try to understand this height will change. So as the speed is increasing, these balls will come like this. Do you agree? And this h will become smaller. If speed is reduced, these balls will come together, like to come closer to each other, and in this case h will increase. So basically h is inversely proportional to the n square in this case. That is what you should know. Okay, so we are basically depending on n square, h is changing, and depending on h your sleeve motion is changing, and depending on the sleeve motion your throttle valve is opening or closing, and that is controlling the fuel supply, and that is controlling the speed of the engine. Is it clear till this? Everyone understood how n and h are related? I'll repeat here. N increases, h will reduce. Okay, I'll say that speed increases because of, let's say, lower load. H will reduce. H will reduce means what? Sleeve will move up. Sleeve will move up means what? It will close the throttle valve. Throttle valve. It tries to close the throttle valve, and it will reduce the supply of the fuel. And if fuel supply is reduced, what will happen? Speed will again will reduce. So in this way, basically, we will maintain the required speed. Okay, and you can do opposite for n reduction. Okay, here it will be just opposite of what we have written. I hope it's clear. So here it is completely depending on the n, no other parameter. If I make a chart for different value of n, how the h will vary. N is in rpm, h is in millimeter. The chart will look like this: 50, 100, 150, 200, 300, 400. Let's say it is h is 358 millimeter, then 89.5, 39.8, 22.4, 9.9, 5.6. What you can see here you can clearly see, if for 50 change in rpm of 50, you can clearly see tremendous amount of difference in h. Change in rpm value of 100, tremendous amount of change in the value of h, around, let's say it's more than 300. But as we move to the higher speed, for the change of 100 rpm, the difference in h value is very, very less. Are you following this? Look at the behavior. This behavior is very, very important. You should understand that though the height of the Watt governor is inversely proportional to the speed, but it's inversely proportional to the square of the speed rather. If you closely look into this equation and basically this chart, you can prepare out of it, and you can conclude that as the speed becomes larger and larger, or the speed increases a lot, then variation in h becomes very, very small. Okay, this shows that this type of governor, the moment of the sleeve will be very, very less at the higher speed. So if I change this speed from 400 to 420 or 430, this 5.6 will not change, let's say, significantly. Okay, so at higher speed, I don't think this will work properly. Correct? So such governors, you cannot, let's say, it's a drawback of this governor, because at very high speed the sleeve motion is very, very less, and it is unsuitable for these higher speeds. So this drawback of this let's say Watt governor is further reduced or resolved by some other types of governors, which are Porter and Hartnell. Okay, so next type of governor which I would like to introduce is Porter governor. Is it clear to everyone how this Watt governor looks like and what are its issues and how it works? Yeah. So I'll go to the next slide now. Write down heading Porter governor. Okay. So in the last class, like we don't have like this kind of bigger sleeve. So what we have done here is we have added some mass to the sleeve. So let's call this capital M. Capital M is the mass of the sleeve, Rest of the stuff is same. Small m is the mass of the balls. Just one new thing we have added is a mass of the sleeve. Okay, so basically now not just centrifugal force, but the force because of this mass of sleeve, that is capital M times G, will also affect. Okay, so this capital Mg will be in downward direction, correct? And if this sleeve moves in upward and downward direction, it will cause a friction on a spindle. So not just um, the one force of the weight itself of the sleeve, but frictional force also will come into the picture. So here the forces are bit more compared to what we have studied previously. Okay, so here capital M is the mass of the sleeve, small m mass of each ball. Okay, F force of friction on at the sleeve. Okay, force of the friction at the sleeve. Okay, what is the force of the friction of the sleeve? Force of the friction always act opposite to the motion of the sleeve. Okay, so whenever the sleeve is moving up, the force will be in downward direction. So total downward force, I would say it's will in that case is mg plus f. Okay, when sleeve moves up. Okay, and when sleeve moves down, the frictional force will be in upward direction. So mg minus f will be the force when sleeve moves down. Okay, our assumption is downward force f will be positive. I hope it's clear. H is the height of the governor in this case. R is the radial distance from the center towards the ball center. And we have other parameters like A, B, and C, which you should know. Okay. So let's draw the equilibrium diagram again at point A. So at point A, how many forces are applying? We have a tension, we have centrifugal force mr omega square, and we have mg. So these three were as before. Apart from that, what we have at point B, we have a new force, that is mg plus or minus f divided by 2. Why divided by 2? Because we are talking about, let's say, focus it, I'll draw this figure it like this. So half of the weight will be taken by this joint B and half of the weight is taken by joint C. So that's why mg plus or minus f by 2. Okay, so I hope you understood here, like why divided by 2 we are doing. So at point B, I would say mg plus or minus f divided by 2. Plus or minus because depending on the motion of the sleeve, either it will be plus or minus f. Okay, so this B point is different, A point is different. So you cannot, let's say, these are not concurrent forces. Whenever we have a non-concurrent force system, we have to take the moments, right? So I have to take the moment at point I, which is which I have used in order to calculate the moment. So moment about point I has to be equal to 0 in order to have equilibrium or the constant speed. It means all the clockwise moment is equal to counterclockwise moment. So we have here only one counterclockwise moment, that is mr omega square times E. Okay, this mr omega square times E. I hope you agree. This is a counterclockwise moment. What are the clockwise moments we have here? Um, Okay. Yeah, Sean, your question I had just gone through. I haven't seen it before, but yes, you are correct. The in case of previous governor which we have studied, the governor is this type of governor is not suitable because it is less sensitive at a higher speed. Yeah, correct. Coming towards the point which I was explaining here, mr omega square times a is a counterclockwise moment, and we have clockwise moments of mg into c plus capital mg. Okay, this is capital mg plus or minus f divided by 2 into c plus b. Okay, yeah. So if you divide with a, what will happen? C by a. Can I write it like this? So this a I am moving here. So I am removing it here and just passing it to the right hand side. So what is c by a? C is perpendicular, a is horizontal. It's a tan of theta. So it's a mg tan of theta plus capital mg plus or minus f divided by 2 tan of theta plus b by is tan of beta. Okay, tan of theta plus tan of beta. Okay. Let's assume a variable k is equal to tan of beta by theta. Tan of beta divided by tan of theta. So can I write, if I go to the next slide, I can write this as, if you take tan theta common, I can write it as mg plus capital Mg plus or minus f divided by 2 times 1 plus k. Okay, because from here if I take tan theta common, so here it will be tan beta plus theta, which is k, and from here also I am taking tan theta common. Okay, I hope it's clear till this. Yeah. Okay, so now tan of theta. What is tan of theta? You can also say it as r by h. Okay, so this is r and this is h. This is also tan of theta. Okay, so r by h mg plus capital Mg plus or minus h divided by 2 into 1 plus k. Okay, and what was on the left hand side? It is mr omega square. So basically here now rr will get cancelled, and this m, if you take on the right hand side, some things also will get cancelled out. So omega square I can write it as 1 upon mh. So m, if you keep it here, I'll just write here itself to avoid rewriting. Omega square will be equal to, this is mr omega square. rr was getting cancelled, so it is mh. Okay, 1 upon mh. Is it clear till this? 1 upon mh times 2 1 upon mh. Yeah, and if I write 2 mg here, I can, let's take a LCM here and write it like this. Okay, just simplification, nothing else. I'm just simplifying the terms. Okay, what is omega? 2 pi n by 60. So 2 pi n divided by 60 whole square is equal to what we can say. Let's take this m inside. I will write this m inside, and I will multiply with a g and divide with g. Okay, and I will write it as g by h 2mg. Okay, g by h 2mg plus capital Mg plus or minus f into 1 plus k divided by 2 times mg, small mg. Okay, yeah, this is clear. So now the 60 term I'll take here, 2 pi term I'll take there. So ultimately, you know, we have already calculated in the previous slide, that is 60 square divided by 2 pi square into g was 895. So same thing I'll do here. 60 square divided by 2 pi square into g is 895 divided by h, and inside we have 2 mg plus capital Mg plus or minus f into 1 plus k divided by 2 mg. Okay, so this is your ns square. So if you remember the same form, what was the previous formula? ns square is equal to 895 by h. Okay, so h is equal to 895 by n square. Here it is quite different. Here we have some more term in combination with it. Okay, here we'll get two different values of the n for the same height of the governor. Okay, because depending on the sleeve motion. Okay, and I'll explain how. Suppose assume that sleeve is moving down. Okay, sleeve is moving down means how much is the force on the sleeve? It is mg force, which is acting in downward direction, minus frictional force, which will be acting in the upward direction. Okay, so this is the total force on the sleeve, which will be in the downward direction if sleeve moves down. Now speed is going down, and sleeve is also moving. Let's say speed comes down, then sleeve also, let's say, comes down, and it is trying to open the wall. And once the wall is open, let's say the speed starts increasing. So if speed starts increasing, the balls would like try to move away from the axis because of centrifugal force. But now the frictional force is there. Okay, so basically this is the frictional force in the downward direction, you can say. And until and unless this frictional force is, let's say, is overcome, the wall will not, you can say, open. Okay, I'll repeat. But now the speed of the increasing engine is, let's say, increasing. The balls will try to move away from the axis, but now the friction has to act in the downward direction. Why? Because I'll repeat. See here, if what condition we have studied? We have studied the condition that sleeve is moving downward. The sleeve is moving in the downward direction. If sleeve is moving down in the downward direction, frictional force will be in upward direction. So mg minus f was the force. But now you're controlling the speed by using throttle valve. So speed is now increasing. Okay. So these balls, whenever the speed is increasing, these balls will tend to move away from each other. And in that case, sleeve is also trying to move up. And the frictional force will be in that case in downward direction, which is mg plus f. Okay. Which is mg plus f. So just you can clearly see that this frictional force mg minus f is now changing to mg plus f. Okay, so basically the sleeve total force on the sleeve is changing from mg minus f to the mg plus f. Okay, and this is mg plus f is now resistance to the motion. Okay, thus until the speed rise to such a level, to overcome this resistance, sleeve will not move. Okay, so basically you have to rise the speed in order to overcome this friction. Then only the sleeve will start moving up, otherwise it will not. Okay, I hope you are getting. Same thing, let's say sleeve is moved up, for example. Sleeve is moved up, so mg plus f is our total force. Okay, um, mg plus f will be our total force. But let's say and speed you are decreasing now. If you are decreasing the speed, sleeve will try to come down. At that moment, at that point, whenever the motion, let's say, tends to move towards the downward direction, the mg minus f will be the let's say resistance of the sleeve. Okay, resistance of the sleeve moment is mg minus f now. So until and unless speed is reduced to such a level, um, so that the force generated is mg minus f on the sleeve, until that point sleeve will not move. Okay, so basically what are the this n square, whatever two values we are getting is are explainable to this mg plus f and an mg minus f. Okay, let me simplify this relationship now. Suppose in this case this theta is equal to beta. What will happen? Theta is equal to beta, k will be equal to 1. Okay, theta, if you are, when theta will be equal to beta, when this c is equal to b. Okay, so obviously what will happen, k will become 1. So this I'll rub this part now. So n square will be look like 895 by h 2m plus 2mg plus mg plus or minus f. 1 plus k will become 2 divided by 2mg. So 2 will get cancelled. I'll not write it, and this is what we'll get. Okay, for k equal to 1, n square will look like this. K equal to 1 means theta equal to beta situation. If the frictional force is let's say 0, what will happen? If frictional force is 0, on top of this k equal to 1, what will happen? N square equal to 895 by h mg plus capital Mg divided by small mg. So gg will get cancelled. So I would say small m plus capital M divided by small m. Okay, this is f equal to 0 and k equal to 1. Friction between sleeve and the spindle, if it is, let's say, 0, so there is a smooth moment. In that case f is 0, and if um, theta equal to beta we are keeping while constructing this, at that situation basically n square is this 895 by h into m plus m divided by m. Okay, so basically what we are doing in this type is we are trying to make it more sensitive, or rather than sensitive, more let's say stable governor we are trying to make. Okay, or um, yeah, okay, we are trying to increase the stability of the governor, making it like uh, little bit sensitive on the higher higher rpm. Also we are making it little bit let's say sensitive on the higher rpm side, okay, compared to the normal Vac governor. What is sensitivity and all, we'll see later. But you should as if now know how the n square is depending on h. Previously it was n square equal to 895 by h. Now 895 by h into some other parameters, because we are implementing the mass of the sleeve, frictional force coming from the sleeve, etc. Okay, is it clear till this? So in case of Porter Governor, our balls are just at the joint of two links. Okay, link OA and OB, wherever it's joining, we have uh, mass of the ball there. Now let's say I'll go to the next slide. Write down heading Flywheel Governor. Okay, this just for your understanding. I will not go into the much details of it. Um, the only difference in this and what we have studied before, okay, is that the where the masses are fixed. If you fix the masses here, it is our Porter Governor. But if we are making a link, again a separate link AE and DF, and on top of that, if you are fixing the masses, then this BAE link and CD link, CDF links are getting created. Okay, so this kind of governor is called as a Proel governor. I hope you agree. I hope you understood the difference. This is more or less similar to the Porter governor, but the masses are fixed here in little upward, not on the joint itself. Okay, so basically it will create little bit different moments. So so here you are not supposed to take the moment, or your forces will not be here. Now your force mg will be here, mr omega square will be here. Okay, and it will not be r now, it will be r dash, because this r dash is little offset. Okay, if it is straight here, that's fine, it will be r. But if it is, let's say, a little bit moved up outward, so if it is straight here, I would have said yes, r dash equal to r. That is a special case of it, but let's say in general case would be r dash and r are different. Okay, this force is more or less same. So same thing you can do here, m r dash omega square equal to mg into how much it is, this distance, how much it is, c plus r minus r dash. C plus r minus r dash. Okay, and plus mg plus or minus f divided by 2 into c plus b. Okay, so only you can clearly see here r dash term is coming and this term is different. Other things are more or less same. So if you take a moment about point I, this is what you will get. Are you following till this? Yeah, it's more or less similar to the Porter Governor. So I'll do the calculation fast now. We'll not go into the more details here. So mr omega square into e, sorry. Okay, because mr omega square into this distance e will create a counterclockwise moment. So e I will take here. Okay, yeah, and for example, let's say this a is vertical, then I can say r dash is equal to r if a is vertical. Okay, so then this r and r dash will get cancelled. So the same thing I can write m r omega square will be equal to 1 upon e m g c plus capital Mg plus or minus F divided by 2 into C by A into C plus B basically. Okay, and if you multiply with A and divide with A, what will happen? C by A here, C by A here, B by A here you will get. Okay, A by E. C by A is what? C by A is tan of theta, B by A is tan of beta. So tan of theta you can take common. Again the same way, mg plus or minus f divided by 2. I will write here 1 plus k because k is tan of theta divided by tan of beta. Okay. What is tan theta? Tan theta can also be written as r by h. Okay, this is a more simplified version of it. Then mr I can take here, mrr will get cancelled. Okay, m omega square will be there on the left hand side, m I can take to the right hand side and I can make it 2mg and then write 2mg here and g also here in multiplication. Omega I can write it as 2 pi n by 60 whole square. So 60 square divided by 2 pi square into g I can bring to the right hand side and I can make it as 895 by h. Okay, a by e as it is into 2 mg plus capital Mg plus or minus f 1 plus k divided by 2 mg. Okay, this is your n square. So here also more or less same thing, but in the last type, that is portal governor, a by e was not there. Okay, if you remember the formula correctly, 895 by h, same thing, mg plus 2mg plus mg plus or minus f into 1 plus k divided by 2mg was there, but this part was not there. So this is an additional part here. Okay, so you should know parallel governor, what is the difference? A by E term is coming here. So if k is, again same thing, if k is I'll go to the next slide. Let me check if I have, oh, yes, I have a blank slide here. If k is equal to 1, let me write it again. N square is equal to 895 by h A by E mg 2mg plus mg plus or minus f into 1 plus k divided by 2mg. Okay, now if k is equal to 1, what will happen? N square is equal to 895 by h E by E 2mg plus mg plus or minus f into 2 by 2mg. 2 will get cancelled, so I'll rub this. This is what you will get. So if f is equal to 0, what will happen? Okay, just f equal to 0, k is not equal to 1. In that case, n square is equal to 895 by h E by E 2mg plus capital Mg 1 plus k divided by 2mg. Okay, here you can rub this g part. Okay, and now let's say if k is equal to 1 and f is equal to 0, n square will be 895 by h E by E. 2 will get, k is equal to means 2 will get cancelled, m plus capital M divided by small m. Okay, so this is more or less same formula, only A by E is different here. Clear? Yeah. So how this Proel governor or Porter governor is different from VAT governor, you should know. Okay, there is just initially we have studied this formula. In the second case, we have added this term, and in third case, we have added A by E term. Okay, so we are each different type comes up with the some different terms here. Okay, yeah. Another type we will study here is Hartnell governor. One more type of governor we'll study here, that is Hartnell. All of these are okay. Um, all of these are centrifugal governors. Okay, these are more commonly used. Hartnell governor. Write down heading Hartnell governor. So in all the previous example, we can clearly see either sleeve is there or and balls are there. Okay. In first case, sleeve mass was also not there. In second case, we have added sleeve mass. In the third case, we have added sleeve mass. On top of that, we have added some offset to the balls. Okay. In Hartnell governor, what we are doing, we are controlling the balls, okay, by spring here. Okay, so you can clearly see here we are using the some spring arrangement here. Inside this spring is there, here you can clearly see. Okay, so I'll repeat, balls are controlled by spring. You can clearly see in the figure number A here. Initially the spring is fitted in the compression. You have the nut here to control the compression of the spring. Okay, on top here we have nut to control the spring compression. We have two bell crank levers here. This is 1 and 2. Okay, each of them is carrying a mass at one end and the roller at other end. So this is roller and this is mass, this ball with certain mass. Okay, we have bell crank levers. At one end we have attached masses, other end we have attached rollers. Okay, and they are pivoted at these points. These are the pivot points. Okay, I'll use the red pen to show the pivot points. Okay. Other dimensions are also given. E is the length of the from pivot point to the center of the mass of the ball. B is the small b is the length of the pivot of the point to the roller center. Okay. Small m is the mass of the ball. All these things you already know. Okay. So what will happen if I let's say uh, run the spindle with a higher velocity? Let's say omega 2. Omega 2 is a higher velocity and omega 1 is a lower velocity. Let's say it is rotating at a higher velocity. What will happen? These masses will go away and sleeve will move up. Do you agree? So this figure you will see, this figure is more or less same, right? This situation is this. So this situation will get at a higher omega. Okay. When omega is lower, what will happen? Omega is lower, these balls will try to come closer and you will get this kind of figure. Okay, so the position of A, B, C is shown here. You should compare with if this is at a lower omega, this is at a high omega. I hope you are following till this. Is it clear? Any doubt till this? The only thing is we have spring force. Okay, so spring force will come into the picture. Apart from, so previously what we have studied, only centrifugal force. Later we have added centrifugal force plus centrifugal force, then mass of the sleeve and the friction force, and now on top of that, spring force will come into the picture. Okay, so let's see here. If you see at point C, we have F2 force. This is centrifugal force because of omega 2 higher RPM, mr2 omega 2 whole square. Okay, and at point B, we have three forces now, mg plus F. Because sleeve is moving upward, frictional force will be downwards. So mg plus F plus Fs2. Okay, Fs2 is the spring force. Okay, in the when omega is omega 2, and in the top situation where we have lower omega, sleeve is coming down, so it is mg minus F plus Fs1 divided by 2. So we are keeping it general. Okay, so I am just writing F, all are plus. Okay, in some case it can be positive, it can be negative, depending on how sleeve is moving. So but the word 1, Fs1, indicates that spring force when omega is equal to omega 1. When omega is equal to omega 2, the spring force is Fs2. Okay, yeah. And this F1 is centrifugal force in the when omega equal to omega 1, and this is centrifugal force when omega equal to omega 2. So if we take a moment at fulcrum A, what will happen? At pivot point, if we take a moment, F1 A1, I can say that in from the first figure, if we take the moment, when omega 1 situation is there, at that situation, I can say F1 into A1 equal to half of mg plus Fs1 plus small f, okay, times B1 times B1, okay, and balls are here, so it is minus how the balls are, okay, balls are also taking a clockwise moment. This is clockwise, this is clockwise, this is counterclockwise, so it is plus mg into c1. C1 is this, okay, mg c1. In when omega equal to omega 2, f2 a2 is equal to half of mg, capital M G, plus Fs2 plus F times B2 plus mg times C2. Okay, uh, let's, okay, it's minus basically because it's a counterclockwise moment. Okay, we can say it like this, but let's say assume that to make it more simple, generally the theta is very very small. This theta 1 and theta 2 angles, they are not too large. Okay, theta 1 and theta 2 are very very small in the working range, so we can say that this a1 is equal to a2 generally, and b1 is equal to b2 generally. So what does it mean? C1 equal to C2 equal to 0. So you can neglect out these two terms. Okay, this and this, and you can make it more general. F1 into A plus F2 into A. Okay. Yeah. A1 equal to A2 equal to A, you can say, and B1 equal to B2 equal to B, you can say, and you can make the conclusions like this. And now if you subtract, what you will get is capital F1, or let's say F2 minus F1 into A is equal to half of MG will get cancelled, FS2 minus FS1 you will get into B. Okay, so from this I can further write FS2 minus FS1 is equal to 2A by B times F2 minus F1. So difference in the spring force is equal to 2A by B times F2 minus F1. What is F2? Centrifugal force in the second case, minus F1 is the centrifugal force in the first case. Okay, if you include the stiffness of the spring and all, Fs2 minus Fs1 can also be written as H1 times S. What is S? S is the stiffness of the spring. And H1 is, let's say, a moment of the spring. How much deformation, how much by how much length spring is moving. So it's a spring, sorry, sleeve is moving. By how much length sleeve is moving. Okay, that is equal to 2A by B F2 minus F1. Okay, so from this I can say S is equal to 2 times H1 into A by B F2 minus F1. Okay. H1 is moment of the sleeve. Moment of the sleeve, if you see here, if I go to the previous slide, the sleeve is, let's say, moving from this distance to this distance, right? It is moving by certain distance. So I can say, so it is corresponds to the radius R2 and R1. Okay. I can say that H1 can be written as theta times B basically. Okay. Or in other words, R2 minus R1 by A into B. Okay. Let me just rub this to avoid the confusion. This part, okay, on the figure. Yep. So try to understand what I'm saying. I'm trying to write H1 value. H1 is moment of the sleeve. Okay. Sleeve will first move, let's say, from here and till here. So certain distance it is moving. Okay. So theta times B. This horizontal distance is B and this is theta. So theta times B will give you this distance. Okay. So that's how I'm writing 2 times H1 is equal to theta times B. Theta times B. And what is theta? Theta is perpendicular. Theta for small angle, theta is equal to tan of theta, you can say, and that is R2 minus R1 by A. So I can say it as R2 minus R1 divided by B, sorry. No, R2 minus R1 divided by A, and B was already there. R1 by A into B. Okay, because I'll write here H1 is equal to theta times B, and theta is R2 minus R1 divided by A, and B is as it is. So that is what I have written into again A by B, and into again F2 minus F1. So this A I can put on numerator. So this A into A will be A square, B into B is B square. So in general, this will become as stiffness is 2 times E by B whole square F2 minus F1 divided by R2 minus R1. Okay. So from this we can say how much amount of stiffness of the spring is required in order to control the forces, centrifugal forces of F2 and F1 value. Okay. So this is also an important formula you should note. Okay. No, you should no need to go through the derivation. You should remember the final answer itself. Yeah. Regarding the frictional force, um, what we can say is, let's say, it's depending on how sleeve is moving. So if sleeve is moving in upward direction or downward direction, frictional force will vary. Yep. Okay. Any doubt till this? Yep. So ultimately, I would not expect you will get like difficult questions from this governor topic, but you should know if um, mainly you can expect the questions from Porter Governor and the Vac Governor, and if you know the relationship between them, you should be able to easily answer the question. Okay, not only just theoretical but also um, numericals you can easily solve. Okay, we are at the end of the session. There are a couple of points which are remain from this topic, um, such as inertia governor. So this is an inertia governor which we'll study in the next week. Okay, how inertia governor works. We also have to understand what is the sensitivity of the governor, what is the concept of hunting in governor. Let me write it. What is the concept of isochronism? Isochronism. What is the meaning of stability of the governor? Okay, and then the last point would be the effort of a governor. Okay, so these are the major points I would expect we'll complete in the next class, and then we'll in the next half session we will study the new topic. Okay, either we'll start cams because three topics are remain for you. One is cams, another one is balancing, and the last one is dynamic analysis of linkages. Okay, yeah, I would expect like we need at least three classes to cover these topics, and then uh, we'll start numericals. So probably next to next week we'll start the numericals. Okay, we'll go through some previous year questions, not only the numerical but also some theory questions as well. Okay, if you have any doubt till this, feel free to ask. Otherwise, we'll end our session here. Okay, if no doubts, then thank you all for joining this class and have a good Sunday, and let's meet again next week.